Yeah, look at this. That's the statement of my chain rule theorem, just repeated on this slide. It's the same statement. It's very good proof. It's a short, straightforward proof, as a matter of fact. As soon as you have this O notation, the proof becomes a piece of cake. I love it. Listen to this. So first, I take this assumption that f is differentiable, which I marked with the asterisk. And I'm just going to expand it with my O notation. Here it is. Function being differentiable means that there is a matrix L, and we even have an exact choice for this matrix. That's the Jacobian. Oh, we can do derivative, doesn't matter. Such that the f of x is f of a plus the linear piece. So this is a fine approximation, my tangent plane, and then this little O piece. That's the differentiability in one line. Of course, it's still some sort of limit of quotients of two norms, but this all hidden here in this notation. We just shoveled it there because just took it all out of the way. Now, that's the line which is implied by the first asterisk. Double asterisk, so differentiability of my g function. The same expansion via O notation is this, where this g, it's another matrix, another derivative. So what I'm going to do now, I'm going to take my h function, which is combination, which is a composition of g and f, and I'm going to replace this fy with f of x. Look at this. So h of x, which is by definition g of f of x, it's a composition. Now, instead of this f of x, I'm plugging this long expression. So this one goes like this. So let me just open this. Yeah. So I replace my y in here with the f of x with its right hand side, and with the help of this expansion, that becomes like this: the g of b, then my g factor, y is the f of x right in here, and here y is replaced with f of x like this. Actually, I said it wrong. I said I replaced the f of x with the right hand side. No, I don't. I didn't do that. My apologies. I just took this second line and I replaced y with f of x in here, and in here. That's all I did. As simple as this. Now time has come to use the first line. If I use, because b, originally b is like so. So f of x take b, it's what happens if you take this piece on the left hand side, and then I can replace this difference by the remaining piece on the right hand side, both in this factor and in this little O notation is my replacement. So this b is replaced with the f of a as it is, right from here. This difference, actually I haven't done it, it's the next step, I just replaced b with the f of a. I'm too detailed in my exposition, as a matter of fact. So this b is replaced with f of a, this b replaced with f of a, and this b replaced with the f of a. And now I'm going to use this line, finally. For this difference and for this difference, I'm going to keep these two terms. Hopefully. That's the one. Yes, it is the one. We'll just look into this. G of f of a, just h of a. When I replace this difference with these two terms, I did the expansion. So the first term in this place gives you these two pieces, g times l times x take a. And now you can already see the feeling why we have the product of matrices, g times l. The second piece of that expansion is right here. And this one, this piece, after I replaced f of x take f of a with these two terms, it's right in here. So I will summarize what just happened. We use the O notation for 2 differentiability given to us, and then I just did some computations where, I just did some computations with the help of these two lines. Now the actual argument comes here. Look at this. Let me just call this little o of x take a with a shorter name, with a w of x. It's some sort of function, isn't it? Why not just give it a shorter name? If I use today's definition to interpret what the little o means, that's the interpretation. It means that this function is infinitesimally small in comparison to this function. That is the expansion. But listen to this. This enumerator function, wx, if I multiply this enumerator function by another g matrix, which is just a matrix of numbers, it's independent of x, then I can equally say that the limit where w is multiplied by extra g factor is also 0. Because if you multiply a limit by a number, if you multiply a 0 limit by a number, the limit also will be number. Which means, if I now interpret this limit thing again with the O notation, it means that this new function g times wx, it's another little o in comparison to x take a. It may be a different function. It is a different function in principle. But it's still little o. Different little o, but still little o. So this whole piece can be just abbreviated into another little o. Well, I can use the same logic, which I didn't explain in this slide, for this piece. And this longer piece can also be just replaced with another little o. And these 2 little o's together can be combined into the, so similarly, this second term with the little o can be, after a bit of an argument, converted into just 1 little o, even though different, but still 1 little o. And when you add them together, these 2 little o's, by this definition, it again will be another, just 1 single little o. So eventually, look what happens. We started with the h of x. In this line, h of a we kept. This piece we kept. The other 2 we combined into a single little o. And in this line, you can recognize different definition of differentiability. Look at this function h near point a. It's the value of the function in the point a, plus linear piece, a fine approximation, and a little o piece. It means that this function is differentiable, and this product delivers the derivative.